this is the first preschool lecture, I would maybe first start with the roadmap, keeping in mind what we're going to do through the two lectures that I have. So, firstly, today I plan to cover some basic differential geometry, which I think would be useful if we want to study GR. So, very basic stuff. I'm not going to go over them because, of course, the purpose of the preschool is just to give you an overview of things, or basically a refresher of things that you might have seen before. So for the part where I'm going to talk about differential geometry, we're going to talk about coordinates and how we define them on a general manifold. And then we're going to look into vectors and how we define vectors in a general manifold. And then finally, we're going to move on to defining tensors on a general manifold. Now, the reason why this is important is because we know that since we're studying GR, in general relativity, gravity is sort of like a manifestation of geometry of spacetime, right? So in that case, we first need to develop the necessary mathematical background to describe this geometry, which is most of the time in regards to describing curved spaces and curved spacetime altogether, right? So in that case, the mathematical tools are here, which is obviously differential geometry, and we need to understand how we define these geometric objects like coordinates, vectors, and tensors on a general manifold that can perhaps give you definitions of curvature and so on. Okay, so this is what we have in mind today. For tomorrow, what I plan to do is follow up from tensors and define special relativity, which is also something that we expect that you've seen before, in the notion of tensors. So how do we write Lorentz transformation with tensor index, or just these forms in tensor notations and so on, which will be hefty when we do GR eventually. So this is the plan for now. So let me go on and start the first lecture. So since we're talking about geometry, of course, the first thing to understand is the background of things, right? If you want to, let's say, define a certain geometry, you have to define the geometry on a particular background, right? And that particular background for general relativity is called a manifold. So essentially, what is a manifold? I'm pretty sure that you are already familiar with the concept. Is there a question? Okay. Okay. So, like I was saying, that I'm pretty sure you're already familiar with the concept of manifolds. However, maybe you have not used the term manifolds before. So, for example, let's talk about what is a manifold to begin with. So, firstly, like I said, we are actually familiar with some basic manifolds, like, for example, Euclidean space, right? Euclidean space, which we write as Rn, is an example of a manifold, where all the points in Rn define all the points in the manifold we're talking about. Also, a circle, let's say S1, which is a unit circle, and let's say a sphere, S2, are also manifolds. So you're already familiar with manifolds as such. Perhaps you have not used the word manifolds for these objects before, but these are all manifolds where all the points in S1 define all the points in that manifold, and particularly as well for S2, you also have all the defined points on S2 defining the manifold points for that particular manifold. Okay, so now you can also generalize this to higher dimensions. So for example, a higher dimensional generalization would be for, let's say, the circle Sn. So for n to be any dimensions you want. So n is n-dimensional sphere. So Sn basically tells you that this is an n-dimensional sphere. And for any other objects, like, for example, if I want to add a torus here, which is denoted as T2, this could be generalized for higher dimensions as Tn. And all of these are actually manifolds too. Okay, so basically what we understand in general about manifolds is that manifolds are smooth surfaces, and they can also be high dimensional generalizations of the background geometry. Okay, so now any type of set that gives you, let's say, points, let's say the set of continuous rotations, for example, can also create a manifold. Lie groups can also create manifolds. Phase space, like phase spaces of classical fields or quantum fields, etc., can also create manifolds as well. In fact, the space of thermodynamic equilibrium states, I mean, we've all studied that before, right? So those states can also create manifolds. In fact, those states can create different points on the manifolds, and you can sort of map all of these points to a particular background geometry. Now, let me define manifolds, not abstractly now, but its particular definition. So, uh, or maybe an n-dimensional manifold M is a continuous space that looks locally like Rn. Now, the different patches of the manifold can be sewn together. Okay, so now maybe a lot of these terms are abstract as of now. Like, for example, what does continuous space mean? What does locally look like? Rn mean? And what are patches, right? And of course, what is sewn together? Now, we're going to address these questions step by step. So, for example, what do we understand by continuous? So, in a general point of view, right, continuous just means that you can draw this particular space without any holes, right? Essentially, it means that this space is defined at all points, right? So therefore, a manifold has to be smooth. Okay, what that means is it has to have all points to be differentiable. That means there are no holes in that particular manifold, number one. Number two is that it looks locally like Rn. Now remember what Rn is, right? Rn is Euclidean space. So from here we get an understanding that, okay, locally this manifold, a generalization of manifold, whatever it is, n-dimensional, has to look locally like Rn, meaning that it has to look locally like Euclidean space, which is also flat space, okay? And now what do I understand by different patches? Now, in GR and in general, when we define a manifold, it is not always possible to find all the points of the manifold to be defined by one singular coordinate system. Okay, so like I said, a manifold essentially tells you it's some background space, right? If you want to think about it like that. So let's say I have a background space as such, okay? And of course, this background space to be determined, it needs points, right? So if I want to describe this particular background space, I will need to describe these particular points on the background space. And the way I can describe these particular points is through coordinate systems, like we do for any system, right? So in that case, it could be possible. In fact, more so, it is seen that we don't have particularly one singular coordinate system that can define the whole of the manifold. We might need more than one coordinate systems to define this manifold. So let's say I can define this patch of the manifold with simple Cartesian coordinates. Let's do very simple two-dimensional Cartesian coordinates, x, y, okay? However, perhaps this part of the manifold is not easily described by x, y, but is described by r theta, which are two-dimensional polar coordinates, right? So now I have definitions of the manifold, but with respect to two different coordinate systems, right? So this is one patch, and this is another patch of the manifold. And what I mean by sewn together is, since the manifold has to be continuous, that means there is no hole or discontinuity in the intersection of the patches. Okay, so this is your formal definition of a manifold. And in general, and in GR particularly, we describe this particular space-time that we live in using a Lorentzian manifold. Okay, so in GR, we have Lorentzian manifolds. And we will understand what that means. Essentially, this Lorentzian manifold actually looks like Minkowski space locally. However, it is different in how it attributes time. So for example, if I have four-dimensional Minkowski space, which I think you are all familiar with because we're guessing you've done SR before, this is just given as R13, right? So you have one temporal part and three spatial parts, right? However, for Lorentzian manifolds, we treat the temporal part with a different signature. Meaning, if you write a distance element, ds squared, as dt squared plus dx squared plus dy squared plus dz squared for a four-dimensional Minkowski space, then for a Lorentzian manifold, a Lorentzian space, we would treat time in a different footing with a minus signature, and space in another footing with plus signature. Okay, so this describes a Lorentzian manifold. This describes four-dimensional Minkowski space. Okay, and I'm saying that a Lorentzian manifold, whatever it is in its generalization, should locally look like four-dimensional Minkowski space. Okay, in fact, this is interesting because perhaps this will be covered in the later lectures. But this is actually the foundation of the equivalence principle of GR, which states that GR locally should boil down to SR, special relativity. Okay. Are there any questions so far? Okay, I see a few questions, but I think they're already answered. So thank you. But okay, so let's move on. Now, moving from here, of course, the natural way to go is to define what coordinates are, right? What are these coordinate systems or coordinates that we're using to define the manifold? So hence, we look into coordinate charts. Okay. So of course, you are all familiar with coordinates, at least the concept of coordinates, and we think of the concept of coordinates as a set of real numbers, right? So whenever we write coordinates, in general, we think of real numbers x1, x2, da da da, up to xn, given that the manifold is n-dimensional. But now we will review the concept of coordinates from a more formal language. Okay, so the definition of coordinates is the following. So coordinates are maps between an open set of points U on M and points on Rn, where I define a map, which is this map that is between the set of points U on M and points on Rn, where this map is the following. So it takes points from U to Rn. Why? So there is a question What's an open set in this context and why does it matter? Okay. So the open set is basically a set of points on U. And the reason why it matters is because we essentially want to have a boundary of U. So let me draw the figure. Maybe that will make it clear. So let's say I have a manifold. So denote this as M. Okay. And there's a patch inside M, which we are calling as U, right? And let's say there is a point on this patch, which we denote as P. And there is, of course, the space Rn, right? So why this is an open set is because we want to define this boundary of the patch. So over here, what this map essentially tells you is that you take a point from U and you map it to Rn. Okay, so you map it onto another patch in Rn. So every point in U, which is a patch in M, can be mapped to Rn using this map phi. Okay, so that is what we're thinking of when we're thinking of coordinates, because these point P's are essentially giving you coordinates on Rn. Okay, so basically, in general, are there any more questions? Yes, exactly. So compactness and connectness. So you need a boundary of U. Basically, you need U to be compact. Essentially, that is what I meant. Okay. Is the expression for Minkowski interval correct? Can you check again? Yes. Well, I would have this if I'm talking about this to be a pseudo-Riemannian manifold. However, I want to consider Riemannian manifolds when I say that you just have plus signatures. Okay. But like I said, we use pseudo-Riemannian or Lorentzian manifolds in GR. So we basically put the minus to treat time in a different footing. Okay, does that answer your question or concern? Okay. Okay, so let's move on. So like I was saying, so this is how we define coordinates. Coordinates are these maps that take any point in the manifold to a real number space, which is Rn. And from here, this map phi, we're going to call this a coordinate chart, which makes sense, right? Because it charts the coordinates on M. And in general, we would require more than one chart to cover the entire manifold. And a collection of all of these charts is called an atlas. So the collection of charts is called an atlas. Yeah, we use C as one. So maybe I should have mentioned it, but I figured you guys were familiar with this. But we use natural units. And I think we are going to use natural units for the rest of the course, where you use G equals to C equals to 1. Okay? Where G is basically the Newton's constant, or the gravitational constant, whatever you want to call it. Okay? So now, for every point P that is in U, you can have a coordinate chart as the following. X1P, X2P, up to XNP. Okay. So you can also write this in shorthand as X mu, where we use mu as to denote the number of dimensions that we have. So mu basically runs from 1 to n. For Euclidean manifolds, which remember is essentially a Riemannian manifold. So it goes from basically 1, 2, 3, 4, 5, 6 up to n. Or you can use mu from 0 with a temporal component, which we determine as 0, to n minus 1 for Lorentzian manifolds. Okay, so maybe for people who did not do SR, maybe this is a little confusing. I don't know. But if you're already familiar with this, maybe you should know that we treat T with the index 0, and all the other space components, let's say in Cartesian coordinates, then run from 0 to 1 to 2 to 3, etc. So for Lorentzian manifolds, where we have a different footing for time, we would use mu0 as the temporal part, and the rest of the spatial part will follow from there. Okay. Okay. Now, another key point to mention over here is that we will always assume that the map is invertible, which means that an inverse map exists and should give you the point P on M. That means that if this map is phi, then an inverse map should exist where it takes the point on Rn and maps it to the point P on M. Okay, so this is the inverse map. Okay, so now another point that I would like to mention over here is that we require that all charts are compatible in the regions of overlap, because as I said, that if you have charts that do not that are not defined in the regions of overlap, you would basically have discontinuities, right? And we don't want discontinuities in our manifold, because that is how we defined it, that it has to be a continuous space, right? So you have many particular charts over here defined in the manifold, and these regions of overlap should be compatible and hence give you continuous space. So from here, you can actually define some particular things. Like if we understand how we map coordinates on a manifold, you can define then functions, curves, vectors, and so on using these coordinate systems like we do for any general mathematical objects, right? We first have the fundamental tool, which are points, and then you use those points to define functions that give you, again, some functional value on Rn, which basically, so if you think about functions heuristically, you would think of functions as machines that you plug in something into that machine and it gives you something back, right? So similar to that idea, you can think of functions over here as it takes in a particular input, which is coordinates. And since coordinate charts are maps, it should take an input from M, which is the manifold, and give you some output in Rn, right? So in that case, we can define the function as also a map. And that map basically takes you from M, which is the manifold, to Rn. So in that idea, we can define a manifold, we can define a function on a manifold in the following way. So function is a map where we have the function to take points from M and land them in R. Okay, so what this basically means that it essentially assigns a real number to each point on the manifold, right? Meaning that you would take any point P over here and you plug that in the machine, which is the function. So you have the machine over here, which is the function. You take any point P, which is in the manifold, you pass it through the machine. It should give you something that exists in Rn or R, right? Where I know that this is the real number space. So of course, if it exists in the real number space, it has to be a real number itself. So hence this machine essentially gives you the corresponding real number to each point on the manifold. So basically, this assigns a real number to each point on the manifold. Okay. Now, moving from here, look at this particular diagram to understand something that I'm going to explain in a bit. But let me just draw this first. So this is the real number, and this is the real number space, which is n-dimensional. Okay. And now the way I'm defining this function is that I have the manifold again, I have the patch U. And like I said, what the function does, it takes a point on M and it gives it back in R, right? So it basically assigns a real number to every point on the manifold. Now, you can have a map that relates to this real number on the real number space, okay? So I know also from this idea over here that the map phi basically takes a point P from M to Rn, right? So in that case, if this is point P, then a map like this would be phi, right? And hence, I can create a connecting map over here that would just be a composite of these two maps. So this is f, the function map, and this is phi, the coordinate chart map. And hence, this map over here would just be a composition of these two, right? However, it would be a little different, where I would write this as the inverse map of phi1. Can anybody tell me why this is the inverse map and not just f composite of phi? So in general, I would think that, okay, if the composition is to take place, the composition should be f composite phi. But why is it not that? And why is it f composite of phi inverse? Can anybody tell me? Yes, exactly. So basically, phi takes you from M to phi. Phi takes you from M to Rn, right? But over here, I'm taking Rn to R, and then eventually, this is where your f function ends, right? So what I am doing is basically inverting the action that I did for phi, because phi basically takes from M to Rn, but here I'm taking from Rn, so it has to be an inverse operation, right? So hence this is phi inverse. Okay, good. So now, next, I want to state something. I don't know if this is important or if it would be used later on, but in GR, such functions are called scalar fields. Well, it's kind of obvious why they're called scalar fields, because essentially they give you, real numbers back. So they don't give you objects that have extra higher dimensions. So in that case, it's obvious why they're called scalar fields. And of course, a function as such is called smooth if f composite phi inverse is a smooth function, or basically a smooth function for any chart phi. Okay. Now, again, like I said, what I mean by smooth is essentially it is differentiable everywhere. Okay. Okay, so there is a question. Is there a convention for a Lorentzian manifold to have an index starting at 0? My question is because I always seen books that they start at 0 and physically 0 is attributed to time. Mathematically, I understand it as being in a degenerate coordinate. I don't know if I'm correct. Well, essentially, so you are partially correct in the sense that we don't obviously treat the space coordinates and the time coordinates in the same footing. Like, for example, the way you translate or rotate in space, you would not be able to do that in time, right? So in that case, 0 is just, it works as, well, I don't know how to explain it, but 0 basically is different from 1 to 3. Right? You do understand why. So in that case, 0 is attributed to time in the sense that when you have just when you're dealing with spatial coordinates, it would be easier to run from 1 to 3, and 0 just runs independently. So whenever we work with components as such, let's say, you're taking derivatives with respect to spatial coordinates as such, you can just do, 1, 2, 3, something like this, where d naught is just for temporal derivatives. Something like this. Of course, you would have 1 by c and so on. Okay. So in that case, of course, this then becomes a degenerate coordinate, right? Because it just it does not translate or rotate or basically transform the same way as the other spatial coordinates do. Okay. So there are many questions. By function you mean f? Yes, f, and also this operation over here, because this would also give you an Rn, which you can again define with another function, f prime or whatever you want. So this is also a function. This is also a function f, but they both give you R, my components in R, which would then be called scalar fields. So this is also a function operation. This is also a function operation. So you can mean either of them or both. Which fn is scalar fn? Okay, so I think I answered that question too. What might happen if the transition functions were not smooth? Okay, this is a good question. So let's say if the transition functions are not smooth, which means that they are not differentiable everywhere. So since we define this to be a differential manifold, meaning it's a smooth manifold, right? This is what we started with, which means this is a continuous space. So that means all points on this manifold is defined. All of them are defined, right? So let's say I have a defined point over here and I'm taking this to R. Again, remember that R is also a continuous manifold, right? We have defined points at all our real numbers. So in that case, if the transition function were not smooth, that would mean that there should be a discontinuity when I'm transporting this point to R over here. But that does not happen, and that should not happen, right? Now, another thing is, let's say, when would you call a transition function unsmooth, right? It is when, let's say, you are transporting it from some region that has a hole to a region that does not have a hole. So in that case, how would the transportation or transition take place from the whole area or the area that has a discontinuity to all points over here that are continuous? That would not make sense, right? So the vice versa can also happen, which means that if, let's say, this is a smooth manifold where I don't have any holes or any discontinuity, but I have discontinuity over here, I would not be able to transport or transition all points from here to here because some of them would be lost where there is a discontinuity. So that would not be a smooth transition. Okay, does that make sense to everyone? So this would not be possible. Well, it could be possible if you can avert this particular discontinuity somewhere, but that is again a topic I think that would be covered in the later lectures where we call these singularities. They could be coordinate singularities where you can just avoid them by considering them in a different coordinate system. Okay. Okay, good. So now let's move on. So now next thing what we want to do, or is a natural thing to do, is we've defined functions, but we want to define vectors. Does non-smoothness be exploited or made somewhat useful? I don't know if it could be made useful, but it is something that we study in GR. Like, for example, well, the most famous example of a non-smooth transition or a manifold that has discontinuity are black holes, right? Because we cannot really probe the singularities of black holes which exist at the center, r equals to 0. So those, if you want to define them using manifold, would have a hole at r equals to 0. So in that case, we do study the behavior of physics around these holes, but I don't know if the transition could be made useful in GR. But of course, we study them using the transition function. So yeah, why not? Okay, so now moving on, like I said, we've defined functions. The next thing to do is to define vectors, because as we understand what we're trying to do over here, which is our goal, is to have the manifold. Remember that this is what we're trying to do, that we have a manifold which defines the background geometry. And the reason why we need the background geometry is to define curved spacetime. And the reason why we need to define a curved spacetime is because we want to study gravity, right? And gravity is a manifestation of curvature. And hence, if we can understand how the curvature works, we can understand how gravity deforms space-time, right? In that essence, we can then use that relationship to derive physics, which would be through the Einstein's equation eventually, which we will do in the latter courses. Okay, so of course, if we have the manifold, only the background geometry is not enough, because we need to understand how the background geometry really affects physics on the manifold, right? So you have, let's say, some geometry over here in the manifold M, but we need to understand how, if you, put something over here, let's say a particle or whatever, how would that behave in relation to the background geometry of the manifold? Because that is what's important to us. Because in physics, we want to see how things are curved or how things are moving kinematically or dynamically or whatever in the manifold. So just defining the background manifold is not enough. We need to see or look at basically vectors, tensors, objects, curves that are on this background geometry. Okay. So does smoothness of function f mean smoothness of the manifold itself? Yes, to some extent, because let's say for this f over here, I'm only defining this f for the patch u, right? But u is not the overall manifold over here. So for f to be smooth for all patches that exist all over the manifold, and if all of the functions that transport all of these patches to R is smooth, then of course the whole manifold is smooth as well. Okay. Okay, so now what we're going to do is we're going to define vectors and manifold. Now, of course, this turns out to be pretty tricky, because in our usual sense of what we understand of vectors, it is not really easy to generalize them on curved spaces, right? Because normally what we think of vectors is just some component that has a certain direction, and this is just some arrow that is stretching from one point to the other. However, it does not really generalize to curved manifolds, because just think about it. When you have, let's say, a flat space, so let me define this as flat space, and this is, let's say, curved space. Okay, my drawing is not really accurate, but I hope you understand what I'm trying to go with. So if this is flat and this is curved, in that sense, if I have a vector that is just an arrow from point A to point B, like this, it would not be the same when I draw the arrow from point A to point B on curved manifolds. You see why this is different, right? Because over here, this arrow would just stretch like a straight line. However, for this curved manifold, it would not be the same. In fact, it would change over how this is transitioning from the point A to B. So depending on what the curvature is and how the background geometry is shaped, this vector would behave differently as it's stretched from A to B. So hence, defining vectors on a manifold is quite tricky. And for that, you need to understand a little bit more concepts to define vectors. So for that, first, what we're going to do is we're going to define tangent vectors, which I think you've already done before, but we're going to define them as tangent vectors along curves on a manifold. Okay, so to define curves, let's look at another image. So maybe let me draw it first and then I'll explain what I'm doing. So you have a manifold. This is a general manifold, and I'm drawing a curve over in the manifold. And again, this is Rn. Okay. And this would map also a curve over here. Now, can you tell me what this transition function is, or the map is that is taking from M to Rn over here? What should I call this map? Yes, exactly. So I would call this phi, right? Because again, like I said, the definition of phi is that something that takes points on M to Rn. Good. So we're going to call this all the coordinate points in Rn, right? Because if you remember, that is how we defined it over here, right? So since this is a curve, so all points on P would be transported on various points on Rn as such. And I'm transporting it from I with a map which is denoted with gamma. Now, this might seem very ambiguous right now, but let me write down the definition of a curve, and then I think it would be more clear. So a curve is defined by the map gamma, where gamma takes points from I, which is this um, I would call I wouldn't call this a space, but okay, maybe like a one-dimensional space or something like that. So I to M, okay, where basically, since I said that this is a one-dimensional space, I can just think of it as an interval, right? So where I is an open interval on R, and this basically means that each point along this curve over here is defined by this particular map. Okay. Now, this map over here has to be parameterized in some way, right? So if I have a curve like this, just imagine that you are moving along some curve on a manifold. So in that case, of course, you have to be parameterized by something, or else what would essentially define your movement from points to points on M? So in that case, this labels each point along the curve gamma by a parameter which we define as lambda, which is again in I. Okay. So if I have a composite map, let's consider the composite map phi composite gamma. What would this give you? Now remember, when we have a composite maps as such, we always read from the left or the right, sorry. So we read from the right. Okay, so gamma composite phi. So this should actually define all points x mu, right? Because remember, if you read from this side, then you have gamma composite phi, which is essentially just this map over here, right? Gamma first and then phi should lead you to define all the x mu's in Rn. So this map is actually this one. Okay. Now this x mu with the parameter gamma describes the curve in terms of coordinates x mu, or basically coordinates on Rn. Okay, is that clear? Are there any questions? Yes, open sets and open intervals are basically similar. So an interval is basically a set too, right? So it's the same thing. Okay, So an open interval, I think for people who don't know, an open interval is when I am not considering the boundary points. Okay, that means I'm not considering the boundary in the interval I. So let's say if I runs from some A to B, maybe like this, it just means that A and B is not included in the domain of I. Okay, this is an open interval. On the other hand, if I'm talking about a closed interval, it would just mean that A and B are included in the domain of I. Okay, that is the basic difference. Okay, so now let's consider a function. And let's say I define a function f, which takes again from the manifold to R, and gamma is again the curve map, right, which takes from I to M. Now, this is a smooth function because if M is smooth, then this transition is also smooth. If I is smooth, then this transition is also smooth, right? So this is a smooth function and a smooth curve, respectively. Then the function along the curve can be defined as the following composite map. So the function along the curve can be defined as f composite gamma as to take from I to R, right? That makes sense because what f does is it takes from M to R, right? And what gamma, the curve, does is it takes from I to M. So if I have a composite function where I have gamma composite f, then of course it should take from I to R. Okay? Is that clear to everyone? Okay, so now moving on. What we want to do next is we want to introduce the coordinate chart using these functions and curves. Because, like I said, it's not only enough to just have coordinate points. We want to define them using curves, like something that is actually moving from point to point on the manifold itself. So in that case, we can introduce the coordinate chart. Should it be gamma composition F or F composition gamma? So this is actually F composition gamma, but the way you read these compositions is from right to left, right? So basically this is gamma first, then F. Okay, and hence it takes from I to R. Is that clear? Okay, so introducing a coordinate chart, remember the chart is called phi. We can write this composite map as the following. Okay, you see why I can do this, right? Because phi inverse phi composition should just take you nowhere, right? Essentially, it's like, because these are inverse maps, if I do phi and then I composite with phi inverse, it should just bring you back to where you were before. So I can write this expanding it, just representing it with phi, the coordinate chart. Okay. So now this part over here, I'm going to write it as fx mu, because if you remember, this is what I have, right? This is what I wrote over there. So of course, this takes from something that is in Rn, where Rn has the coordinates x mu. And this one, I will write as x mu lambda, because if you see this map, this takes from Rn over here in the curve notation, which is parameterized by lambda. Okay. So basically, this is what I have. Now, the coordinate chart just defined with respect to the curve. So essentially, this is the coordinate representation of the function along the curve. Okay. The next thing we want to do is, of course, we want to see how this curve changes, right? Essentially, we have a curve, fine, but that's not enough for us to do physics on the manifold. Because if you remember, the most fundamental thing we do in physics is basically track evolution of a system, right? So in that case, if you have a curve, it's not enough to just define the curve, but it's also necessary to define how this curve changes with respect to whatever rate of change that we're considering. So in this case, since the curve is parameterized by lambda, in that case, the natural extension would be to find a derivative with respect to the parameter lambda, right? So now what we do is we take the derivative of this coordinate representation of the function, which is given as f, which is a function of lambda, with respect to the parameter lambda, which gives the rate of change of the function along the curve, right? So this should give you a rate of change along, or no, of the function along the curve. Okay, so of course, we define a typical derivative with respect to lambda of this coordinate representation. And this would just be equal to the function along the curve, which is parameterized by lambda. Okay, like I wrote over here. Now, this thing is called the directional derivative, which I think you are all familiar with. And it makes sense, right? Because what do we understand by a typical directional derivative? Basically, it is the rate of change along a particular direction, right? And in this sense, that is what we're trying to do, is that we're trying to figure out the rate of change of this function along the curve, which is parameterized by lambda. So we are taking the rate of change along the parameter lambda, which could be thought as of, we could think of this as some direction, which basically probes how the curve is directed in that essence. Okay, so hence, if you have this curve, which again, remember is general because we have not defined what the parameter lambda is. So this is just a map of the curve. So in that case, this could be easily generalized to any type of manifold we want because they can, because here we are not really dealing with particular coordinate systems. We're not dealing with particular types of manifolds. We're actually generalizing to any m, and therefore this derivative should work for any m. And the reason why this is important is because if you've done vectors before, you understand that directional derivatives are very important when we're defining vectors, right? So if this particular directional derivative, which works for any manifold, this could be generalized easily to the case of a curved manifold, right? And that is what we're essentially targeting, right? We want to assign vector descriptions on a generalized curved manifold. So let's consider again another picture for us to understand what I'm going to say next more easily. So let's again do the IMAP, which is again an open interval. Do we have any question? But this is changing on every point. How can we can call it a direct derivative? It's not a direct derivative, it's a directional derivative. Okay, a directional derivative is basically when you're taking a derivative with respect to one of the parameters that is defining the curve. Yes, of course, it will change. It will change as you move along the curve. It will change as you move along the curve. And in fact, that is the most interesting part of the generalized directional derivative because, okay, let me explain this a little bit more intuitively. I think that would be easier to understand. So, of course, this curve is parameterized by lambda, but lambda is not a constant or anything like that, right? It's a parameter that should change as you move along this P, right? So what happens is this directional derivative change as you move from here to here to here to here and so on along the curve, right? So in that case, what you really need to do right now is if you want to define this directional derivative further, you need to define these changes in the way you're moving along the curve, right? And we understand that these are basically tangent vectors, right, on every point. So that is what we're going to do next. We're going to define the tangent vectors, which we will use, well, we will use the directional derivative to define the tangent vectors next, okay? So you've actually held on a very good point that since the derivatives are changing, these tangent vectors are now more essential. Okay, so are the derivative of the function elements of the dual space? No, it's not elements of the dual space. We will actually talk about covectors in a bit, like in just a moment. Okay. So now where I was is here, where I was drawing a diagram. So I have again the interval, my manifold, and there's the curve. I will explain that in a bit, the covector and whatever I was talking about. Just spoilers from whatever I'm going to talk about next. Okay, so just hold on. So this is the generic diagram that I have, and let's say that this is the tangent vector VP at the point P, and again this is R, and this, if you remember, is what map that takes from I to R. Can somebody tell me? No worries. No worries. Can somebody tell me what this map is that takes from I to R? Yes, exactly. So this is F composite gamma, right? And this is, of course, gamma. And this is F. That is what we know. Okay, so now I have the diagram done. From here, I will define the tangent vector, which is VP, as you can see from here. So the tangent vector to the curve gamma at the point P is defined by the following. Is actually d by d lambda okay, which is defined as df by d lambda. Okay, so now this doesn't actually mean that this is a function of f. It just means that VP is acting on f. Okay, this is a particular notation. I don't know if you're familiar with this, but this just means that VP is acting on f. And the way we define the tangent vector is following from here. So like the point that someone raised, that it is changing. Of course it is changing. And in fact, you can see the change via this derivative over here, that VP is not actually a constant term. right? It will change as you move along lambda. So therefore, like you can define any point on this manifold over here along the curve, you will have different VP depending on how your lambda is changing. So the tangent vectors are definitely not stagnant, they're changing. And the way we define the tangent vectors is through this, where we can see that any function will satisfy this relationship. So f is arbitrary. And we can see from here that VP, we can actually define it as the operation d by d lambda. Okay. And you can think of this as the vector, or basically think of this vector as a linear map from M to R. Okay. So in that case, this is what we define. Now, maybe this is a little ambiguous to a lot of people. Why did we bring up this? But there is actually a proof that you can show that VP can actually be used as d by d lambda, where essentially that is what I'm doing, right? I'm acting VP on F, which is basically this operator or the derivative operator acting on F. Okay, so here, in that essence, we write VP as d by d lambda. Okay. Now you can prove this further. Maybe I will keep this as an exercise for later on, or maybe we can discuss it next class. Okay, we can actually prove a couple of things from here. Okay, so I'll move on. And what I mean by linear is, I think somebody also asked this question. Yeah. So what I mean by linear is a couple of things. In fact, this tangent vector does not only satisfy linearity, it also satisfies a property which is called the Leibniz rule. Okay. So the definition of the tangent vector satisfies two important properties. One is that it is linear. And what this means is that if you have the tangent vector VP acting on a combination of objects as such, where f and g are functions, but a and b are just real numbers, then it will act linearly on the functions. No, sorry. Okay, so maybe do the brackets that denote that VP is acting on F and VP is acting on G. Okay. And here, F and G are functions, and A and B are just real numbers. So of course we understand why, right? You see, VP is just from this definition over here is just the derivative operator, d by d lambda. So of course we know that if we have d by d lambda acting on a combination of functions as such, we can take the numbers out and denote it on the functions directly. And hence it satisfies linearity. Okay, it basically acts linearly with the functions over here. Linearly means, well, basically this operation over here. Okay. Now, second property that it satisfies, why do we call gamma for both curve and transformation? Well, basically, okay, so, okay, maybe this is not clear, but so I is an open interval, right? What does an open interval mean? It basically means that you have a set of points. So these set of points actually give you the set of points that are on the curve, right? So whatever transportation that I'm doing over here, taking the points from I to M over here will basically define my curve on M, right? So that's why I'm calling this gamma, because all of these points are transported to um, the curve. So let's say you have a set of interval. Let's say you have 1, 2, 3, 4, 5, la da da, up to n. Okay, just a very basic example. Now, all of these points will be transported to one point on the curve, right? So if these are all, let's say, gamma 1, gamma 2, gamma 3, so I would basically transport 1 to a point over here, which is gamma 1, gamma 2 to a point over here, and so on. So essentially what this would give is basically a set of gammas, right? And all of these maps would also be a set of gammas. So essentially what it would make eventually is the set of gammas on the manifold. So that is why you can call this curve gamma as well. I hope that is clear. Okay. Now, where I was, okay. So another important, yes, of course. Okay, so another important property, yes, you can think of I as R1 because it's an interval, a set of intervals. So just one dimensional real number line. You can think of it like that. Okay, so the second property, which the tangent vector abides by, is called the Leibniz rule. Leibniz or Leibniz, a lot of people call it Leibniz. You can call it Leibniz if you want. But it satisfies Leibniz rule, where it basically means that if you have VP acting on a product of functions, this would basically act on one of them while leaving the other one, and then act on the other one and leaving the previous one alone. Okay, so this is essentially the product rule that we know of derivatives. And since we define VP as derivatives, of course, it abides by this rule. Okay. So now we can use these properties to prove that the set of all vectors at a particular point P forms an n-dimensional vector space called the tangent space. So all of these properties will give rise to the idea that all vectors at point P forms an n-dimensional vector space, which is called the tangent space. Okay, and the tangent space is actually denoted as TP M. Now, a couple of things to note from here and also to understand. One is that the vector space is n-dimensional. Do you know why this is n-dimensional, or it should be n-dimensional? You can, of course, prove this. However, without proving it, can you intuitively guess why it should be n-dimensional? And not anything else. Well, you do understand where n is coming from, right? N is essentially the dimension of the manifold. If you remember, that is what we started with over here, right? So n is basically the dimension of the manifold. So therefore, what I'm trying to say is that if I have an n-dimensional manifold, then the tangent space that is made at point P or any particular point should also give rise to a tangent space that is n-dimensional. Okay, number one. Number two is that you see that I've written tangent space as TP. It means that in one particular point P, you will have a tangent space TP. That means over the whole manifold, at every point, you would have a different tangent space. So therefore, you can have multiple tangent spaces defining the manifold, and then a collection of these tangent spaces is called a tangent bundle. Okay. So now, of course, let me write this down first, that a collection of vectors at each point on the manifold defines a vector field, which is obvious, right? Because all of these vectors should create a vector field. And the set of all tangent spaces of the manifold, not just at P, but everywhere on the manifold, of the manifold is called a tangent bundle. Which we denote as T. Okay. Okay, so moving on, let's consider basis vectors. Okay, so let me define basis vectors as E mu, where mu runs from 1 to n. So here I'm not really considering 0 for now, just on the space, okay, on the manifold. So therefore just the spatial indices 1 to n. So let this be a set of basis vectors. So remember that they need not be coordinate basis particularly, but just basis vectors in general, okay? And this bracket does not mean that this is a an operation or it's acting on anything. It's here just to tell you that this is not a component, but this is just a set of n vectors, okay? So basically you have E1, E2, E3, and so on. So this doesn't mean that this is a component E1 or etc. Okay, this is just a set. So using this basis vector, any vector can be expanded as the following, where we can write it using the help of the basis vector as follows. And I think most of you have seen this before, where we have just dropped VP. Okay, so the way we've defined it was P, but now we're just generalizing for any point. So therefore we dropped the subscript P. Now this expansion V mu over here, this is the component of the vector V in the particular direction mu, which is either 1, 2, 3, etc., depending on which dimension you're talking about. Okay. And if we define this to be the coordinate basis particularly, then this is defined as del mu, and the components then become V mu is equal to dx mu d lambda, which actually comes from the following definition of the tangent vector as dx mu d lambda del mu. Now this relationship, I have not shown this, but there is a very nice proof of this relationship from here. And I want to leave this as an exercise, but you can find it in Bauman's book, which is also one of the references I used to make this lecture note. So the proof is there in Daniel Bauman's GR book. But I would like you to try this as an exercise. Okay, try to define the tangent vector from here and show that this relationship is true. Okay. So now, of course, V over here is this definition that we said right earlier. And V mu is the component which comes from this relationship. And of course, if the coordinate basis is del mu, then this relationship holds. Okay, is that clear? And now what we have is we have a definition of vectors on the manifold. So we've defined vectors on the manifold, which again, remember, is very generalized because we have not defined the type of manifold. So this should work on any generalized manifold we're talking about, whether it is curved or flat. So, and we're particularly interested in curved manifolds. So this should also work for curved manifolds as well. And particularly because you see that the coordinate basis over here is del mu, right? Which is interesting. Like if you think about it, I'm saying that the coordinate basis is essentially some change with respect to mu, x mu. Now, if you're not familiar with this notation, maybe I'll write it down. This just means the partial derivative of del by del x mu. Okay, so that means that I am sort of defining the coordinate basis as some change with respect to x mu, which does not really take place in a flat manifold. Like if you think about it, what are the bases? Bases are basically what defines the dimensions, right, in a manifold. Now, if you want to heuristically understand this, let's say if I have three-dimensional flat space, which is defined in Cartesian coordinates, the basis vectors are just I hat, J hat, K hat for 3 dimensions, right? So basically this defines the direction X, Y, and Z, respectively. So these are your bases. Now, whenever you're dealing with something like this, you don't actually see a change in I hat, right? So what I'm saying is that let's take this example again. So you go from A to B, right? And you connect a vector which stretches from A to B. Now, the way you're moving from A to B, you can define a certain basis vector, defining the direction of movement from A to B. Now you see that this doesn't really change when you go from A to B, right? It is always directing in the same direction. However, if you have a curved manifold now, which we started with, if you remember, and then you plot again your vector from A to B, now you see that this actually you have a change in direction when you're moving from A to B. So hence the basis vectors are actually the change that is administered as you move from one coordinate point to the other. And hence this definition actually makes sense for a general manifold. Now, if you boil this down to a flat manifold, let's say you're working on flat space, this should just boil down to 1, right? Which is exactly the unit vectors. Okay, so let's now define covectors, like I was saying. Can you send us this as an exercise on Slack or email where we need to send some solution? Sure, but I would basically shared the note so you can take a note. This isn't part of the this is not part of the problem sheet, but this is just a fun exercise I want you to try. So if you're willing to do it, you can do it. And the note is there. Okay. Why there exists no unique tangent space, but a set of tangent space on any point in a manifold? Oh, okay. So the reason that is so is because you see that each VP is different because it is defined by E mu over here. And maybe that will be clear. Like the explanation I just gave, E mu is changing as you move along from point A to point B, right? So at point A, you would not have the same E mu as you would have at point B. So in that case, the tangent space that I would create, which would have the basis vectors E mu defined on some point P, would be different than the tangent space that I would have at point B, which, let's say point Q, which is defined by a different E mu. So maybe write this as E nu. Okay, so you understand that is the reason why exactly that you would require different tangent spaces at different points of the manifold, because now we're considering general manifolds and we consider that the basis vectors are different. as you move along from point A to point B. So in that case, all of these tangent spaces would exist and they would be independent. Maybe independent is a strong word, but they would be different from one another. And hence, all of these tangent spaces would just be a collection of tangent spaces, which we call a tangent bundle. Okay. So now, since we've defined vectors, would you like a break of 5 minutes? I don't know if your brain is braining, but I mean, you've been listening to me for almost 1.5 hours. Maybe we can take a break of 5 minutes and then we can come back and finish the rest, which we don't have much left of, just go vectors. And okay, so good. So let's take a break of 5 minutes. We come back at 8:32, if that's okay. I'll see you guys in 5 minutes. I mean, not see, but yeah, you'll hear from me in 5 minutes. No, there is not no network issue. We're just taking a break for 5 minutes and then we'll start in 2 minutes or so. Okay, so let's start. Again, I hope that um, break helped. Okay, so since we've defined vectors on manifolds, the next thing to do is we introduce the associated covectors. Okay, so covectors. And these are also called dual vectors, or basically just vectors with downstairs index. And you will see a lot of them when you do GR. Okay, so you can see from here, we've defined the components of vectors using upstairs indices, right? Now, their dual counterpart, we will just denote them with downstairs index. And in fact, if you have an understanding of vectors and covectors, then the generalization of tensors will kind of be straightforward eventually. Okay, but I think we will cover tensors tomorrow, sorry, on the 28th, because we don't really have much time. And I've been blabbering for a long time now. Okay, so covectors, what are they? In fact, you have actually worked with covectors before, but you probably gave them different names. For example, if you consider just typical linear algebra. So in linear algebra, if you consider a two-dimensional vector, which is living in some vector space, let's call that V, you would write that vector as V1, V2, something like this, something like a column matrix, right? A covector is simply the transpose of this vector. So you can write this as V transpose as V1, V2. Okay, so this is essentially the covector, which is associated with the vector. And of course, it lives in a dual vector space, V star. So a covector lives in a dual vector space, V star. Okay, and the inner product, which actually tells you a lot about the relationship between vectors and covectors. So inner product of a vector and a covector can then be written as the following. So let me write this as U transpose, just to uniquely define the covector and vector. And this would be U1, U2, V1, V2. And there's a matrix multiplication between them. And this would give you the summation, which goes from I1 to 2 of Ui, Vi, which would live in the real number space. Okay, so basically what this tells you is that when you have an inner product between a vector and a covector, it essentially gives you a number, a real number. Okay, now furthermore, you can remember or familiarize with yourself with another definition of covector that you've done already, which is in special relativity, where if you remember, we defined V mu's as eta mu nu V nu as such. And these are essentially the components of a covector. You see downstairs index and so on. We have questions. Slack, email. Okay, can somebody help with the Slack email, Michelle, maybe, or
Yeah, on
someone? Okay. Okay, so if the field of the 2D vector space is complex, then should the covector be only transposing the vector? which field of the 2D vector space is complex? I didn't mention that anywhere. I mean, you would not just transpose it, you would just do a complex conjugate, right? But in this case, we're just dealing with real numbers because as you saw that all the maps are to real spaces. So in that case, it should give you a real number. I think that is the question you asked. Okay, so like I said, that in special relativity, I think you've also familiarized yourself with these notations. And V mu over here is just components of a covector. Okay, and for this as well, you can define the inner product of a vector and a covector as u dot v. And this equals to, I mean, we know this already. Special relativity, the indices run from 0 to 3 for a 4-dimensional Minkowski space. And you would get the following. And this would also be in R. Okay. Again, this would just mean that the covector u mu maps the vector v mu to a number u mu v mu. Okay. Now, let's finally and formally define what a covector is. So we understand what it is, but let's define it. A covector is a linear map from a vector space V to R. So you define a covector with omega, and this basically takes a component or basically an object from V, a vector space, and transports it to or maps it to R so that when the covector acts on V, it should be in the real number plane. Okay. And of course, the covectors omega live in the dual vector space V star. Okay. And of course, since this is a linear map, it will abide by linearity like we talked about before. So being a linear map basically means that if you have omega and it is acting on AV plus BW, where again V and W are vectors and B are just real numbers, it would look like the following, like we had for VP, remember? So VP was a vector, which was a vector, like in its general definition. And omega over here is a covector, and this is also linear. So therefore, it satisfies linearity similarly. Okay. Okay. Now, next thing we want to do is we've defined a covector, and we also said that these covectors actually live in a dual vector space V star, right? So in the concept of our manifold and in its particular context, we know that all the vectors live in some tangent space TP, right, at a particular point P. So in this case, the covectors in a particular point P would actually live in the dual of the tangent space, which we call TP star. Okay, so covectors would then live in the dual space of TP, which is called TP star. Okay. Yes. UV real, of course, real. You see. We're only working with the real space. Okay. Now, moving on, let's now consider the definitions of the covector like we defined for the vectors. And of course, next what we want to do is we want to define the relationships between these vectors and covectors. Okay, so let's again consider f, the function that takes from M and maps it to R. And let it be a smooth function again. Now we define the covector as df by the following. So we have df acting on v is actually v acting on f. Okay, this is a definition with v in, of course, the tangent space TPM, right? Now we pick a v as such where we say that this is equal to E nu, okay? But if you remember, we can set it as d nu as a coordinate basis. So in this case, E nu is a coordinate basis. And specifically, let's also choose a function f as x mu. Okay, so what we're trying to do now over here is we're trying to see what this essentially means, what this definition actually means, by taking a particular example where we set v, the vector, as just the coordinate basis del nu, and taking f as x mu, just a very simple example. Okay, so in that case, the equation above over here then boils down to dx mu from here, right? Which is acting on del nu, on v, which is del nu. And this should equal to v, which is again del nu, acting on f, which is x mu. Okay. Now, like I said, del nu is just del by del x nu, right? So therefore, this would mean that I am acting del by del x mu on x mu. And what should that give me? This is pretty basic, right? It should just give me the Kronecker mu mu, which just essentially means that if you have del x mu derived with respect to del x nu, if they're different coordinate points, and of course, if they are different coordinate points, it would mean that mu and nu are not equal, right? If they are different coordinate points. And hence, obviously, different coordinate points are independent of each other. And if they're independent of each other, their derivatives with respect to each other would give you null, 0. And if indeed they are equal, that means that x nu is the same as x mu, and deriving with respect to each other would just give you unity, like 1, right? So hence you would get the Kronecker delta. And this actually gives you a very strong statement. That means that the dual, or basically covectors and vectors, when they are acting on each other, gives you the Kronecker delta, right? So if we identify dx mu as the dual of the coordinate basis del mu, then the dual of any general basis would also satisfy, basis of a vector would also satisfy the same attributes, right? Which would mean that if I have an upstream index, which you remember as a vector, right? A vector basis, basically a basis vector, which acts on a co-vector or co-basis vector. As such, basically it's dual, right? I should get the Kronecker delta. So therefore, every covector can actually be written with the dual of the basis vector. So if you remember, we expanded V as the following, right? We expanded V as writing it with respect to its component and its corresponding basis vector as such. So therefore, if I have this relationship, that means that the co-basis vector over here is essentially a basis vector with index that is downstairs. That means that in that particular context, I can expand a covector using these dual basis vectors, right? So that is exactly what I do. And hence, every covector can then be written as omega expanded as omega mu, e mu. Okay. So over here, omega mu with the downstairs index is the covector component, right? And I can explain this further by seeing that the action of a covector on a basis vector will be given as follows. So what I mean by that is if I have a covector and I want to act it upon a basis vector, I can expand the covector as such. Let's write it as the following, which acts on the basis vector, right? So this part is just the expansion of the covector, and this part is the same as we had before. And of course, this acts on this, which means that I would then get the Kronecker delta, and hence I would get the following expression, omega nu delta nu mu. And this asserts the fact that mu over here are the same as mu. And this would just boil down to omega mu. Okay. So that means that if I act a covector on a basis vector, it extracts the corresponding component of the covector, okay, which is a very important result. Now, similarly, if I have a covector acting on a general vector, which I write it as such, okay, so omega acting on V, here I can expand V in its general definition. And therefore, I would have this. Remember, this is just a component, so omega acts on the dual basis vector. And hence, this part should give me omega mu, as we've shown over here, right? So this would just be omega mu, V mu. And basically, this is the way we write an inner product, right? So when a covector acts on a general vector, it just gives us the inner product of a vector and a covector in its components. So this is the inner product of a vector and a covector in its components. Okay, so basically these relationships we will use further to sort of make an analog towards tensors eventually, which I think we will do tomorrow because we are already running out of time. So tomorrow what we're going to do is we're going to follow up from here, sort of make a general notion of tensors, and then use tensors to define or basically brush up on special relativity. And then we're done. That would end the lectures for the preschool. And hopefully that should equip you for the lectures that are coming in the main school. Okay, so are there any questions so far? Okay, are there any questions? So 28th. The next lecture is on the 28th, same time, 7 p.m. to 9 p.m. So the lecture notes are up on Slack in the channel, which is called Lecture Notes. So if you have not joined that lecture note channel yet, please do, because I think all the other lecturers will also publish their notes there, which would be helpful if you want to follow through the course. And I've already uploaded mine. basically the one that I followed today. The reference that I use for this lecture note is Daniel Bauman's GR, which is an excellent book. I personally really like it. So if you want, you can read the book. There are many chapters that are very well explained and very concise if you want to have a very thorough revision on GR or SR or etc. And yeah, so I guess we can end today's lecture. Are there any other questions? Oh, so where did I write it? Oh, right. So it's basically because of this notion over here. Because essentially, if you have a covector acting on a general vector, it should give back the Kronecker delta. That is why. Okay. It is defined as such because it works. So essentially, the relationship that is should be upheld over here is that when you have a covector acting on a vector, it should give back the Kronecker delta. And this particular definition exactly gives you that relationship. Okay. Yes, Daniel Bauman's GR book is available in the internet. You just have to type in Daniel Bauman, General Relativity. And it should be right there. Okay. So there won't be problems to practice for the preschool part. However, we will have problems for the main school part. So for the preschool part, you just have to follow the lectures if you want a thorough revision of what is to come ahead, or at least, have some prerequisites done and so on. Book name is this that I've written over here. Okay, dual vectors, geometry objects. So I can pick any linearly independent element in dual space as basis. It doesn't depend on the basis of vector space. We don't have to satisfy the Kronecker filter rules. They exist irrespective. Yes, they would exist irrespective of them, but the Kronecker delta relationship is basically when you act a covector to a vector. So the dual space is independent. Of course, it's an independent vector space, but this relationship should be upheld between a covector and a vector. For what? Worth for what? Is anything other than how vectors and dual vectors interact algebraically worth remembering, conceptualizing, visualizing? For now, I don't think so, because whatever I've covered so far should basically help us naturally extend towards tensors. And that is the main goal, right? Because in GR, that is the basic tool we use to encapsulate all degrees of freedom of a manifold. So in that case, we need to study tensors, but of course, if you want to go towards tensors, we need to first build upon it, and that is what we're doing over here. Yes, exactly. You can actually think of them as bras and kets. In fact, bras and kets are vectors and covectors, which I actually skipped. It is in the lecture note that I gave you, but I skipped it because I thought 2 examples were enough. But you can, of course, take a look. They're there. Okay. Now, if everything is done, maybe we can end this session. Thank you all for joining. I'll meet you guys again on the 28th. Okay. So Michelle, I think you can stop the recording.
Okay, perfect. Thank you, everybody. See you guys.
Thank you. Goodbye. See you again.